Hi, my name is Brandon Graisley. I'm a high school math teacher. We're learning about the reciprocals of quadratic functions. We already learned about the reciprocals of linear functions and how the x-intercept of a linear function turns into the vertical asymptote of the reciprocal function. And so we have a bit of a complication with quadratics. They can have multiple x-intercepts or maybe none at all. So let's just write that down. Since a quadratic function has 0, 1, or 2 x-intercepts or zeros, its reciprocal, its reciprocal function, can have 0, 1, or 2 vertical asymptotes. And I'm just going to draw a few quick sketches of what that can look like. So I'm going to show you what 2 vertical asymptotes looks like first. And then we're going to get into how the equations work out. So let's say you had a parabola, a quadratic function that looks something like this, crossing in these 2 spots right here. Those are the 2 x-intercepts. Well, those 2 x-intercepts are going to produce vertical asymptotes for the reciprocal function, like that. So the new function will not cross those lines. It is discontinuous at that spot. And so what we have is this negative bit right here turns into another negative bit in the reciprocal function. It'll do something like this. Approaching, it goes asymptotic here, down to negative infinity. And this upper part looks like this. Asymptotic to the vertical asymptote there, and it also goes to 0 on this side. And over here we get this. There we go. So that's the basic shape that we're going to get. So this is when we have 2 distinct zeros, and that gives us 2 distinct vertical asymptotes. So that's one version. So another version is we could have just one x-intercept, one vertical asymptote as a result. So let me draw another sketch. And so let's say in this case we have something just very slightly different. The parabola touches in a single spot. Its vertex is on the x-axis. Well, in that case, that vertex on the x-axis does give us a vertical asymptote because it is equal to 0, which gives us a 0 denominator if we were to include that in our domain of the reciprocal function. And the reciprocal function then is going to kind of stay positive here in this example because this is entirely above the x-axis. So it's like that middle piece is sort of missing and the other 2 parts get smushed together, and this has only one distinct 0, and therefore we get one distinct vertical asymptote. The 2 that we had here can't be separated anymore. They're pushed together. And there is one more possibility. And that is that we get a parabola that doesn't touch the x-axis at all. So what if we have something like this, for example? It doesn't have any zeros, or another way to say that is there's no place that if you take the reciprocal of the y value that you're going to get an invalid or undefined number, like 1 divided by 0. So what happens in this case, and this depends a little bit on what these numbers look like precisely, but let's say this was the number 1, the reciprocal of 1 is 1, and you're going to get a shape that looks like this. Now these are touching in this specific example, but that's not always the case. Sometimes they don't touch at all, and sometimes they cross over each other, but we'll see that in a little bit. So this is the kind of thing that can happen when there are 0 zeros, no x-intercepts, and no vertical asymptotes. All right, so let's work through a long specific example. These do take a moment. So let's say we have an original function. Well, actually, I'll just show you the reciprocal version of it. So here's the reciprocal of a quadratic. It's 1 over, and then the bottom is the quadratic part, -1/2 times x plus 1 times x plus 3. So that's quadratic, and it's in factored form, which is the easiest form for us to use because we can identify the zeros. So let's start by doing that. First, we're going to find out what are the vertical asymptotes. I'm sorry, when I said zeros, I meant the zeros of the quadratic part. They're not zeros of the reciprocal function. They're going to become the vertical asymptotes of the reciprocal function. So first of all, these occur when f of x is not defined. Now, it's not going to be defined because that's 0 on the bottom. So when the bottom is 0, the denominator. So that's -1/2 times x plus 1 times x plus 3 would be equal to 0, because that would make this become 1 divided by 0. That is undefined, the function is undefined. So whatever numbers we come up with here that would make this equation true, those are not going to be part of our domain. They are the new vertical asymptotes. And so what must those be? This happens when x is -1 from this one, or x is -3 from that one. So each of these is a vertical asymptote. So we have 2 vertical asymptotes for this one. Now we want to see kind of what happens as we approach the asymptotes on each side. Now I already drew a quick picture, but let's maybe do a quick table of values to show what happens. So I'll do a chart here, maybe is the best way to show this. So as x approaches is sort of one side of our chart. I'm going to fill in some values here. And what happens to f of x? F of x goes to or approaches something else. So we're going to fill this in. I'm not going to show you all the calculations, just the idea. So let's do the one on the left first, which is -3. It's the one on the left of the graph. So as x approaches -3, now that's not enough by itself, because we have to know, are we approaching the vertical asymptote from the left side or the right side of that vertical asymptote? So we're going to need to look at it from the left and also separately from the right. Now, one way to do this is to just test a number that's a little bit to the left of -3, like -3.0001. And you put that number into your equation, and you see what you get. So, not too hard to do, but just pick a number, and I really mean it. Just grab a calculator and stick a number just a little bit to the left of -3, and you're going to find out that you get a very large negative number, because this goes to -infinity on that side. If you approach it from the right hand side, it goes to +infinity. So you test this just by trying out some numbers is kind of the easiest way, or you can imagine what happens as you approach here. Maybe I'll just grab my diagram from before to show you for a minute. This one's not quite the same because it's upside down from what we're dealing with now, but this one goes to +infinity. And you notice all the values are actually positive here all at the same time. There's no crossing over the x-axis, so testing any value on that side is actually okay. But it's good to pick one really close by so that you're more confident. Looking at the other asymptote, that was at -1. What happens on the left of -1 and what happens on the right of -1? And we see that it goes to +infinity here and -infinity there. Again, just test some values if you're not certain, and that'll give us our behavior of the graph around the asymptotes. Now, we also have to worry about horizontal asymptotes. So horizontal asymptotes, those occur when you go extremely to the left or right edge of the graph as x goes to positive or negative infinity. And we could have included this all in one of our charts here, but I'm just going to make a new one. Same thing, but now we're wondering what happens when x gets very, very negative or goes to negative infinity versus positive infinity. And what we see is that in both cases they go to 0, but what we have to wonder is, are we coming at 0 from above or from below? That's the thing that we wonder. And in this case, they're both from below. And you can actually infer that from our graph or from our chart up there. But another way to do it is to put a really big number in, like -1,000,000 or -10,000 in for x and see what you get. Do you get a negative number or a positive number? And same thing for positive. As you move towards positive infinity, put like 10,000, positive 10,000 into the equation, and you see you'll get something close to 0, but it'll still be negative, so that means we're approaching from below. Okay, well, let's start graphing what we know so far about this curve. Let me grab a color here. First, let's put the vertical asymptotes on. There's one at -1 and one at -3. So let me move over this way a little bit. So just a dashed line is the way we usually show this. And ideally in a different color from what you're going to draw your curve in. So mine's in pink here. So that's my vertical asymptote. And I'm even going to label it just at the bottom here. That's x equals -1. And another asymptote at -3. So x equals -3, I labeled it at the bottom as well. So we know that the curve is going to be kind of moving around and sort of getting close to these asymptotes from different sides here. Now we saw that, and we're going to do a kind of an accurate sketch, not super accurate, but we saw that as we go towards -3 from the left-hand side, we were going to negative infinity. So our curve is going to be kind of down this way. I'll just draw the arrow down there like that. And the same thing was true as we approached -1 from the right-hand side. The curve is like that. We're going to connect this all up in a minute. The other thing we saw was that approaching these from the inside, so -3 from the right goes to positive infinity, and -1 from the left goes to positive infinity. So it's going to curve down in the middle here like this, and on the sides we're going this way. Let's talk about the horizontal asymptotes. Both are approaching 0 from below. So that means it's going to curve up and over this way. It's not going to cross the axis, it's just going to go in that direction, and the same thing is true over here. So let's talk about extreme points, maximum and minimum points. And here's the big idea, is that the only local, in this case it's a minimum, is halfway between the vertical asymptotes. And it corresponds to what would be the vertex of that, just that quadratic, if it wasn't a reciprocal function. So what's halfway between the two vertical asymptotes? Well, let's just see that midpoint is, or the halfway x value. That happens when x is, we take -1 and we add to it -3 and we divide by 2. So that's the way to calculate that, but in this case you probably could have just figured out it's -2 is the halfway point. So let's see what that is. So f at -2, we're going to calculate the y value now. Now our original function was 1 divided by -1/2 x plus 1, so that's -2 plus 1, and then x plus 3, -2 plus 3. And we should see a really nice pattern on the bottom here, if we've done this correctly. 1 over -1/2 times, looks like that's -1, and looks like that's +1. You should always see that nice pattern, and when you're finding this halfway point between two zeros, on the denominator, or 2 vertical asymptotes in this context. Looks like we're going to have a positive number, right? 2 negative values down here. And that's a half times 1 times 1. That's 1/2 on the bottom. 1 divided by a half is just 2, and that's a positive 2. Okay, I'm going to grab my graph here. So when x is negative 2, my y value is positive 2, and that's going to be a minimum. Now here are my little, as I approach the asymptotes here, moving asymptotically. So I'm just going to sketch these in here now like this. It's actually that probably wasn't the best sketch. I should have gone a little more extreme than that. Let me just fix that kind of. It should be kind of squarish looking, not this one. More squarish looking, okay? All right, let's talk about intercepts. So we've talked about 2 different kinds of asymptotes, extreme points. Let's see about intercepts. Well, we already know there are no x-intercepts, for the same reason that there were no x-intercepts for reciprocals of linear functions. There's no way to get 0 out of that when you have 1 divided by a number. So no x-intercepts at all, that's not possible. For y-intercepts, or for the y-intercept, we evaluate f at 0, which in our case is 1 divided by negative 1/2 times 0 plus 1 times 0 plus 3. And let's see, that's 3 times a half. So negative 3/2 on the bottom is negative 2/3 overall. Okay, so let's grab this and see how that works. Negative 2/3 is about there. So I'm going to aim for that spot when I'm drawing my curve there. Okay, how about the domain and the range? Well, the domain is the set of all x values that are real numbers such that x is not equal to either of the vertical asymptote numbers. So not negative 3 and not negative 1. So that's it. Those are the only 2 values that are missing. We have a complication for the range though, because even though we're not done drawing this yet, we're going to see that all of the x values down here, or sorry, the y values down here are all filled in, there and there. But the y values up here, the function is going to kind of come down, curve through here, and then go back up. It doesn't drop below this value 2. That is, there's no function anywhere in here. No matter how far left and right you go, there's nothing between 0 and 2. So that's going to be what's missing in our range. So I'm going to describe the range. Rather than saying what's missing, I'm going to say what's there. Y is an element of the real numbers such that, now I want to say that all of the bottom part is in, all of the, basically all negative numbers. So I'm going to say y is less than 0, not equal to though, it has to be strictly less than 0, no x-intercepts. So that's true, or y is greater than or equal to 2, that local minimum that we found. So all the negative numbers, and then 2 and up for the positive numbers, not 0 anywhere though. Maybe it's time to just kind of finish drawing this curve in here. We're just doing a sketch, so I'm not super worried about it being perfectly accurate or anything like that. Not too bad. We want the same kind of shape on this side. It is, after all, symmetrical. If you wanted to, you could even kind of map that point over there. Oh, I did pretty good actually. Feel good about that. And so, a little hard to tell, I can't really zoom out here very well, but that is the curve. So the bottom part makes these 2 kind of L shapes. They're upside down or sideways here. And then we have this U shape in the middle, and apologies about that little bit that I messed up on there. So that's what the curve looks like. So let's talk about where the curve is increasing and decreasing. We're going to look at the intervals. So I'm going to make a little chart. The interval and then we're going to look at the slope, or the sign of the slope, along each important interval. So the important intervals we had were from negative infinity to negative 3, and then there was the bit from negative 3 to negative 2. Now the reason I stopped there and not all the way at negative 1 is because that's our minimum point. That's a key point that we're going to need to look at. I'm going to look at the specific negative 2 to negative 2 interval. It's just got one spot in it. So I used square brackets to include that number. Round brackets excludes the number negative 2. But I could have just said x equals negative 2 right here instead of calling it an interval. Negative 2 to negative 1. That takes us to the next asymptote. And then negative 1 to positive infinity takes us to the end. Let me just divide this up. And I'm going to grab my sketch and kind of stick it in here from time to time. When we're looking at this left-hand part, what does this look like? This is a downhill section. It's dropping all the time. The slope is negative. If you were to draw a tangent line, it would be with a negative slope. So the slope is negative for the first bit. Now, from negative 3 all the way down to this spot at x equals negative 2, that is also decreasing. So negative. But at 2, or yeah, at negative 2, I'm sorry, that's the minimum, and so the tangent line there would be horizontal, and there would be no slope there, or the slope would be 0. After that, we start going uphill, positive slope. And last, from negative 1, as we move this way, the curve is moving upwards. It slows down a lot, but it still has a positive slope. So that's the sequence we get of positive and negative and 0 intervals when we analyze this function. Okay, let's see another example. Suppose we have the function f of x equals x minus 2 squared plus 2, and the reciprocal function is g of x is 1 over f of x, so 1 over x minus 2 squared plus 2. Okay, so what's going to happen when we do this? Well, let's maybe do a quick sketch of this original function so we can have some idea of what's going to happen here. I'm not going to put quite as much detail into this one. It's going to be a sketch with key points rather than a super detailed example. So this original function, this is in vertex form, so its vertex is at positive 2, positive 2, so I'll say that's about there. And I notice from the a value here, which is 1, that this opens upwards. So that's the original function, y equals f of x. So this is the reciprocal of that function. Now this one does not touch the x-axis, which means there are no vertical asymptotes in it. I am going to just, this is not an asymptote, but I am going to just put a quick marking on here to show you where the axis of symmetry is for this function. So that's the axis of symmetry. I didn't mark that on the last example, but you could have, because we're going to see that same symmetry in our new curve. So let's see, that's the y value positive 2. The reciprocal of that y value positive 2 is the y value positive 1/2, which is right there. Now from there, this curve moves up, so the numbers get bigger, 3, 4, 5, and so the fractions down here are going to be 1/3, 1/4, 1/5, and so on. They get smaller. So they're just going to go this way, approaching the axis like this, but never touching it. And so this is y equals g of x. Now what's that point right there? That came from the reciprocal of 2, or you can just substitute the number x equals 2 into here, and you'll get 1/2. So that point there is the point 2, 1/2. So because this was in vertex form, I could see right away that it wasn't going to cross the x-axis. So I didn't have to calculate the zeros. There weren't any zeros. So this one's actually a lot simpler to deal with, and we don't need quite as much detail. Now you might want to just think about what the range might be. So that's one of the things that's an issue. The range is the set of all y values that are real numbers such that, well, actually it's pretty limited. It goes from positive 1/2 down to 0, but doesn't include 0. So I'm going to say 0 is less than y, which is less than or equal to 1/2. So very limited range. It doesn't get very tall here. Nothing in the negatives at all, and nothing above 1/2. All right, let's discuss strategies for finding the vertical asymptotes. So the easiest kind, I'm going to call this number 1, is if the denominator is factored, like if it's in a factored form of any kind, the zeros of the denominator of that quadratic are the vertical asymptotes. So if you find out like x equals 5 would make the bottom 0, then x equals 5 is a vertical asymptote. There might be only one, but there could be 2 if it's in a factored form. So that one's pretty nice if it works out that way. So another possibility is if the denominator is not in standard form, of course you wouldn't do this if you've already got factored form, but if it's not in standard form, for example it's in vertex form or just jumbled up, not normal form, then you can expand that form if necessary and simplify to get standard form. That's the old ax squared plus bx plus c. Yeah. Now at that point you can continue with number 3 here. Maybe I'll just write that down. Go to step 3. So if it's not in standard form, get it there. And now that you're in standard form, we can do this. We can try to factor to find the zeros of the denominator, or use the quadratic formula to find the zeros of the denominator. Those are your two choices, and sometimes there will be no zeros, and that'll be okay. So let's write down just a few examples of how we can do this. Let's say your function was like 1 over 2 times x minus 5 times 2x plus 1. If that was your function, call that f of x. Then the vertical asymptotes are x equals positive 5 and x equals negative 1/2. Both come from just using these factored binomials on the bottom. If we had a different function, like g of x is, let's say, 1 over negative 2x squared plus 18, then we can rewrite that as, let's start factoring, negative 2 times x squared minus 9. Looks like that's 1 over negative 2 times x plus 3 times x minus 3. And so from there we get the vertical asymptotes are x equals 3, or maybe I'll write negative 3 first, and x equals positive 3. So both of those were just using some factoring. Well, one was already factored. Another possibility is you get something like this. h of x, sorry this is a little messy, h of x is, let's say 1 over x squared plus 2x minus 6. 6 is 2 times 3, 1 times 6. We're not going to be able to factor this, but let's see if the quadratic formula works out for us. So I'll just write that down. The quadratic formula is that x equals negative b, so negative 2, plus or minus the root of 2 squared, that's 4, minus 4 times 1 times negative 6, all over 2 times 1 is 2. So x is negative 2 plus or minus, that's going to be 28, so root 28 over 2, and that simplifies to negative 1 plus or minus root 7, taking a 4 out of there and the square root of it. So that gives us two answers as well, negative 1 plus root 7, negative 1 minus root 7. Those are the asymptotes. And one more possibility, I'm kind of low on room, maybe I'll just jam it in over here. You could have something that won't work out. So for example, if I make something like 1 over negative 5 x minus 2 squared, that's a parabola opening down, so if I make it drop down as well, the vertex, then that's never going to cross the x-axis. And so there's not even any need to expand this. You can just recognize by knowing your vertex form that this thing is going to open, the parabola is going to open downwards, not cross the x-axis, so the reciprocal function won't have a vertical asymptote. Alright, so that was a lot to deal with. The big idea though is to find the vertical asymptotes, if they exist, by thinking about the zeros that correspond to the denominator quadratic. Once you have those vertical asymptotes, you can go ahead and work on sketching out the function. Remember, three types, one which has this cap or cup shape, like the one we did, one that has sort of just two L's, and one that has this little cusp here, this bit that pops up and then drops back down again. Okay, so that is your introduction to reciprocals of quadratic functions. Thanks.